what do you mean by a chemical bond? Look here. One or more electrons attracted by more than one nucleus. Try to understand this definition. One or more electrons attracted by more than one nucleus. What is the essential difference between an atom and a molecule? Atom and a molecule. In an atom, you have only one nucleus. One nucleus attracting one electron. Electrons are under the influence of one nucleus only. In a molecule, the electrons are under the influence of more than one nucleus. In a hydrogen molecule H2, you have two nuclei and two electrons. Both the electrons are attracted by both the nuclei. Whereas in an atom, there is only one positive, one nucleus. You will see more than one positive. Therefore, now you say these two hydrogens are bonded, or you can look at that way also. Electron is holding the nuclei. This electron is attracting both the nuclei. So, this electron is bringing the nuclei together. How do two positive charges come close? This is positive, this is positive. How can they come close? They don't come close. A negative charge will bring them together. They are brought together by a negative charge. So, one or more electrons attracted by more than one nucleus is bonding. And what are the important things in the examination point of view, especially in competitive exams? We will be facing some questions like this. Number of pi bonds in SO3. How can you find? For which you need to know the structure, and for that purpose, first things first, what we will do is how to draw any structure. Let us learn how to draw any structure. At least this covers most of the structures. Hydrogen HFCl, O minus, they always form one bond. I will explain myself later. They always form one bond means when they are terminal atoms. For example, in PCl5, chlorine is said to be the terminal atom. Phosphorus is the central atom. Phosphorus is at the center and 5 chlorines are approaching. These are called terminal atoms. So, when hydrogen is a terminal atom or any one of these is a terminal atom, what they do is they form one bond only. And oxygen forms, wherever it is as a terminal atom, two bonds. And any plus in a group, the role of any plus in a group is to accept a pair of electrons. A lone pair of electrons. Plus, if you have a positive species, it accepts a pair of electrons. And any other minus other than O minus, we have already mentioned what O minus is capable of. O minus can form one bond. Any other minus other than O minus donates a pair of electrons. Donates a pair of electrons. Now, let us apply this the simplest possible way. SO3, how to draw the structure of SO3, and through which only you know how many pi bonds are there. Sulfur is the central atom. How do we know which is the central atom? Whichever is one is central atom, obviously. There is only one sulfur, that is center. And a host, it's like a host. And 3 oxygens. What is the role of oxygen? We already discussed. Oxygen forms two bonds. over. Now we have got 3 sigma and 3 pi bonds. SO3, 1 sulfur, 3 oxygens, each of them forming 2 bonds, SO3. Now, let us PO4 3 minus. Phosphorus is the central atom here. P O4 1 2 3 4 PO4 4 oxygens, but 3 of them are minuses. The formula itself suggests 3 minus. So minus, 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 O minus. So out of the 4 oxygens, only one is an oxygen atom, the other 3 are O minus ions. And what is the role of oxygen? You see, oxygen forms 2 bonds. I am just translating what I have written there. O minus forms 1 bond, 1, 1. Over, that is the structure of PO4 3 minus. Anyone can draw by just applying simple procedure. Now, SO4 2 minus, how will you draw? 1 sulfur, 4 oxygens, 2 of them are minus. Out of the 4 oxygens, 2 are minuses. Oxygen forms, what is the role of oxygen? 2 bonds, 2, O minus 1. So don't worry whether sulfur can form 6 bonds or not, 1, 2, 3, 4, 5, 6. Don't worry about it yet, it's too early. Now, BF4 minus, BF4 minus. Now, 1 boron, 4 fluorines. It is all there in the formula. I am not using anything from outside. Whatever is given in the formula, I am just spelling it out. I am just spelling it out. 1 boron, 4 fluorine, one of them is a minus. Fluorine forms 1 bond. F minus, what is the role of minus in a group? Whenever there is a minus donates a pair of electrons to the central atom, minus. And this is called a coordinate covalent bond. Whenever somebody is donating a pair of electrons, so BF4 minus. Next, NH4 plus, NH4 plus, 1 nitrogen, 4 hydrogens, one of them is a plus. What is the role of hydrogen? Hydrogen forms 1 bond. What is the role of plus in a group? What is the role of plus in a group? A plus accepts a pair of electrons. Plus is accepting a pair. Okay. Now, this is the first principle. What is the first principle? HFCl, minus, they form 1 bond. Oxygen forms 2 bonds. Plus accepts a pair of electrons. Next, 2. More than one central atom. Suppose there are more than one central atoms, then distribute all other atoms equally. Distribute equally. More than one central atom, distribute equally. Cr2O7 2 minus. Cr2O7 2 minus. You have 2 chromiums, 7 oxygens, 1, 2, 3, 4, 5, 6, 7. Cr2O7 2 minus. Look here, I will write it again. So, more than one central atom distribute equally. Cr2O7 2 minus. So, now you have 2 chromiums and of course 7 oxygens, 2 chromiums, 7 oxygens, 1, 2, 3, 4, 5, 6, 7. The 7th one is also equally distributed. Whatever is there, that has to be equally distributed. And 2 minus, 2 of the oxygens are negatives, distribute them also equally. Now, what is the role of oxygen? Forms 2 bonds. 2. O minus forms 1 bond. 2. 1 each, that's all. Cr2O7 2 minus. So, more than one central atom distribute equally. That is the second instruction. Third, for nitrogen, suppose you have more than 3 bonds. You need to have one dative bond. For nitrogen, more than 3 bonds, one of the bonds should be a dative bond. I tell you what. NO3 minus, 1 nitrogen, 3 oxygens, one of them is a minus, NO3 minus. 1 nitrogen, 3 oxygens, one of them is a minus. Oxygen forms 2 bonds, O minus forms 1 bond, and therefore, what is the nitrogen? The quota of 3 bonds are over. The quota of 3 bonds are over. Therefore, this must be a dative bond, coordinate covalent bond, like this. Fourth instruction being, try to avoid lone pairs as far as possible from a structure. Try to avoid lone pairs as far as possible. You know why? The lone pairs repel the bond pairs and cause strain to the geometry. 5. For oxy acids, what are oxy acids? Acids which have both oxygen and hydrogen. Acid that has both oxygen and hydrogen. H2SO4 is an oxy acid. H3PO4 is an oxy acid. For oxy acids, number of OH groups is equal to number of hydrogens present. There is the matter. Of course, we have nearly 60-70 oxy acids, and in the case of just 3 of the acids, they are an exception. H3PO3, H3PO2 and H3BO3. Of course, H3BO3, there are 3 OH groups. You have 2 OH groups only here, 1 only here. 3 hydrogens are there, 3 OHs are there, but that is an exception for some other reason. Now, H2SO4. How will you draw the structure? H2SO4, 1 sulfur the central atom, and 2 hydrogens. Number of OH groups is equal to number of hydrogens present. Since you have 2 hydrogens, you draw 2 OH. What else you are left with? 2 oxygens. 2 oxygens, they form 2 bonds each. H2SO4. That's all. As simple as that. Now, H4P2O7. H4P2O7. What is that? You should notice there are 2 phosphorus atoms, 2 central atoms are there. 2 phosphorus, 2 central atoms. How many OH groups are there? The number of OH groups is equal to number of hydrogens present. 4 hydrogens, 4 OH. 1, 2, distribute equally. 3, 4. 1, 2, 3, 4. And 3 more oxygens. 1, 2, 3. What is the role of oxygen? Forms 2 bonds. 2 bonds. 1, 1. That's all. For oxy acids, number of OH groups is equal to number of hydrogens present. Now, why is H3PO3 an exception to that rule? That is in fact not an exception, and that is a part of a huge generalization. Let us see what that is. H3PO3, 1 phosphorus, 3 OH groups is what you and I would like to write. This is how we would have liked to write POH thrice. This is how we wish it is. Okay. But the structure of H3PO3 is not this, because after forming 3 bonds, phosphorus is left with a lone pair, a pair of electrons unused. And to avoid that lone pair, we had an instruction earlier, avoid the lone pairs as far as possible. Therefore, a little change in the structure. P double bond O, OH, OH and H. This is it. So one of the hydrogens is directly bonded to phosphorus, so that phosphorus can have a tetrahedral geometry and it can get rid of its lone pair. Now H3PO3, H2S2O7. How will you draw the structure? 2 sulfurs, 2 central atoms. Recollect the rule, more than one central atom distribute equally. Since you have 2 sulfurs, 2 OH groups, 2 OH, and you have a total of 7 oxygens and 5 more oxygens are left, distribute equally. 1, 2, 3, 4, 5. 2, 2. What is the role of oxygen? Forms 2 bonds and O once again acting as a bridge. H2S2. So that's all about how to draw any structure. Using this, we can almost write all our level structures, if not complex structures. This could be drawn. Next, how to find hybridization. And in that structures part, you must have got a doubt. Sir, we have seen a few elements like hydrogen, fluorine, chlorine, bromine, iodine, and just oxygen and O minus. How 1, 2, 3, 4, 5, 6, with just 6 or 7 elements, how can you say any structure? There are 80, 150 elements. The reason is most of them are metals. Out of the 115, 80 odd are metals, and they don't generally form covalent bonds. I mean, metals mostly form ionic bonds, they don't form covalent bonds. Therefore, structure is there only for a covalent bond. And in a covalent bond, only non-metals participate, noble gases in any case don't participate in bonding. So, what are the other non-metals we have? Sulfur, phosphorus, carbon, silicon. And carbon, sulfur, they are in most cases, they are the central atoms rather than terminal atoms. Carbon will never be a terminal atom. You will never see a compound called ClC3 where carbon is the terminal atom. Okay. Therefore, the rarest exception being sulfur, carbon disulfide. It is of course similar to carbon dioxide. Okay, CO2, CS2, all in the same. So, though we have learned a few elements, 1, 2, 3, hardly 5, 6 elements, we are saying that we can draw any structure using this knowledge. Okay. There may be 1 or 2 cases you may not be able to apply, but that you should not be worried about that, because 99% of the structures is made possible. 1 or 2, okay. Complex structures you may not be. Suppose you may not be able to draw B4O7 2 minus, that Na2B4O7 borax, and you may not be able to draw the structure using that principle, B4O7 2 minus. We have to learn one or those two separately. Most things you learn in a general way, and if there are any 1 or 2 things out of the ordinary, you learn them separately. That should not be a big problem. How to find hybridization? Most cases, H is equal to V plus M minus C plus A by 2. Don't worry about the hugeness of this formula. It's no big formula. This application is quite simple. V is equal to number of valence electrons of the central atom. Most cases that is group number. Number of valence electrons of the central atom. In most cases it is group number, except in the case of xenon, because xenon happens to be in the 0 group, but the valence electrons are 8. So for this purpose we say xenon belongs to 8th group as far as this question is concerned. M is number of monovalent atoms. Number of monovalent atoms, that is You should not consider monovalent terminal atoms. You should not consider species like oxygen. Forget oxygens. Just forget oxygens. Ignore oxygens. SO3, the 3 oxygens are not counted at all. Then C is cationic charge, charge of a cation. Means suppose there is some positive charge, as a positively charged ion, you subtract the charge, A anionic charge. Anionic charge. This is some kind of a shortcut, no doubt, I agree, but we need a procedure, and this helps in finding almost 99.99% of the hybridizations. After doing all this, H is equal to 2, you will get sp, 3 sp2, like that, so on and so forth. 4 sp3, 5 sp3d, sp3d2, sp3d3, as the case may be. Okay, you can proceed to answer that. Now, apply this for, start with NH3. NH3. What is the hybridization of nitrogen in ammonia? The question will be, the hybridization of nitrogen in ammonia is. How will you find that? Valence electrons. Nitrogen belongs to the 5th group. That's why I said group number is extremely important. 5 plus monovalent atoms, 3 hydrogens. Hydrogen is monovalent, means which forms one bond. This M has not much of a meaning. This M suggests you don't consider oxygens, consider all others. 3 hydrogens, you have to consider them. 5 plus 3 minus 2. 5 plus 3 by 2, it is equal to 4. The hybridization is sp3. So, the hybridization of nitrogen in ammonia is sp3. What I mean to tell you here is, though the formula appears to be very big, its application is very simple. 5 plus 3 by 2. What about this C and A? When the question is about cation, this C comes into picture. When the question is about an anion, ammonia is neither anion nor cation. It is not charged. NH3. Next, SO3. SO3. Sulfur belongs to 6th group. 6 plus 0 by 2. 6 plus 0. Why 0? Oxygens are not considered. 6 plus 0 by 2, 3 sp2. Like this, you can apply this formula any number of cases. Then NH4 plus, NH4 plus. Nitrogen, number of valence electrons 5. 5 plus 4 minus 1 by 2. Valence electrons 5 plus 4 minus 1 by 2. 5 plus 4 minus 1 by 2. How much will that be? Okay, sp3 once again. Now, SO4 2 minus. Valence electrons of sulfur 6. Oxygens, forget. Ignore oxygens. Therefore, 6 plus 0 plus 2 by 2. 6 plus 0 plus 2 by 2. So, after all said and done, 6 plus 2 by 2, 8 by 2, 4. sp3. Now, PCl5, phosphorus. You should know that phosphorus belongs to 5th group. The group number is extremely important. 5 plus 5 by 2. 5 plus 5 by 2, 5 sp3d. So, one big hurdle, how to find hybridization of any molecule. So, you can apply this in any number of examples. SOCl2, the hybridization of sulfur. How to find that? Central atom is sulfur, 6, oxygen 0, 6 plus 0 plus 2 by 2. 6 plus oxygens are not considered. Since you have 2 chlorines, you take 6 plus 2 by 2, sp3 once again. XeO2F2. 8 plus 0 plus 2 by 2. What is this 8 plus 0 plus 2 by 2? Xenon has 8 valence electrons. Oxygens are not considered. So, 8 plus 0 plus 2 by 2. 10 by 2, which happens to be 5, sp3d. 8 plus 0 plus 2 by 2. So, how to find hybridization? So, what is that we have done so far? How to draw any structure, how to find hybridization. And for carbon only, this is for carbon only. For carbon only, no pi bond. Suppose you don't have a pi bond. Since we have to find the hybridization of large number of carbons in organic chemistry, we need to have a special procedure for carbon. No pi bond, the hybridization is sp3. 1 pi bond, the hybridization is sp2. 2 pi bonds, the hybridization is sp. What does it tell you? Pi bonds are eating into pure orbitals. Pi bonds are consuming pure orbitals. They don't want hybrid orbitals. So, carbon is forming 1 pi bond means it has got 4 orbitals and you have to leave 1 orbital, one p. The other, that p, using that p, a pi bond is formed. No pi bond, sp3. Now, let us try to find out the hybridization of each of the following. What about this carbon? It has got 1 pi bond, sp2. What about this carbon? This carbon has 2 pi bonds on either side, sp. 1 pi bond, sp2. 1 pi bond, sp2. 1 pi bond, sp2. 2 pi bonds, sp, 2 pi bonds, sp. That's all. 2 pi bonds. So, whenever carbon is not forming a pi bond, it is sp3. Next, valency is of 2 types. Valency, 2 varieties. One is electrovalency, covalency. Electrovalency, covalency. What is electrovalency? The number of electrons lost or gained by an atom. The number of electrons lost or gained by an atom, of course, in an ionic bond. Number of electrons lost or gained in an ionic bond. Now, covalency is the number of electrons shared. Number of electrons shared by an atom. Number of electrons shared. So, this electrovalency will be obvious in compounds. MgO, magnesium is losing 2 electrons, oxygen is gaining 2 electrons, Mg2 plus O minus. But this covalency is somewhat hidden. We have to find this out. So, covalency is equal to number of bonds formed including dative bonds. Including dative. Dative means coordinate covalent. Dative bonds. So, the covalency should include the number of dative bonds also. So, how to find the maximum covalency? Maximum covalency. What is the maximum covalency of nitrogen? What is the maximum covalency of phosphorus? Whenever such a question arises, how to find that? First of all, unpaired electrons. Unpaired electrons. Suppose there are unpaired electrons in the electronic configuration. When you write the electronic configuration, if you come across unpaired electrons, Unpaired electrons are used in sharing and covalent bonds are formed. Covalent bonds are formed. Unpaired electrons are used in sharing, covalent bonds are formed. 2. Paired electrons. Suppose you have paired electrons. What will you do with a pair of electrons? They are excited if possible. If possible in the sense, if there are vacant orbitals. Excited if possible, and more covalent bonds are formed. More covalent bonds are formed. If not, suppose it's not possible to excite the electrons. Suppose it's not possible to excite the electrons because of the non-availability of any vacant orbitals, they are donated as such. Donated to form dative bond. Remember the warning, only one pair is donated. Only one pair is donated. Vacant orbitals. Suppose you have vacant orbitals are used in accepting pairs of electrons, and dative bonds are formed. You accept until you get a maximum of 6 bonds. Until you accept pairs until you get a covalency of 6. Let us apply these rules. So, unpaired electrons are used in sharing, covalent bonds are formed. Paired electrons are excited if possible. If not, they are donated as it is. The pair is donated. And vacant orbitals are used in accepting pairs and more dative bonds are formed. Now, let us apply this with beryllium. Beryllium. 2s1, 2px1, 2py0, 2pz0. The original configuration of beryllium is 1s2, 2s2, and its ground state it is 2s2. In its excited state itself it is 2s1, 2px1, 2py0, 2pz0. Look here. Beryllium has just 2 electrons in its outermost shell. What we believe about beryllium is it better forms ionic bonds, loses the 2 electrons to somebody, becomes beryllium 2 plus ion, and we prefer beryllium to form ionic bonds. It's not our preference that is important. What beryllium does is important. Look here. Why doesn't beryllium generally form ionic bonds? Since it has only 2 electrons after it loses beryllium 2 plus, what happens? Once it loses 2 electrons, it has 4 protons versus 4 electrons. Look here, 4 protons versus 4 electrons. So, if it loses just 2 electrons, it becomes 4 protons versus 2 electrons. Means too much of positive charge and there is an imbalance of positive and negative charges. Therefore, beryllium doesn't prefer to form ionic bonds. And our textbooks say when beryllium forms beryllium 2 plus, it becomes a very small ion, and small ions are more covalent. Okay. So, when beryllium ion is formed, it develops covalent character. It doesn't mean that it forms beryllium ions and then it develops covalent character. To start with, it is covalent. It has a covalent tendency. When you read the statement from books, what you misunderstand is beryllium forms Be2 plus ions and then since beryllium 2 plus is very small because of huge positive charge, 4 units of positive charge and 2 units of negative charge, Be2 plus is very small, and small cations are being more covalent, they may make you believe that first beryllium 2 plus is formed and then covalency is created. It is not the case. Beryllium straight away doesn't prefer to form ionic bonds because losing 2 electrons is very difficult for it. Now, so what does beryllium do? It has got 2 electrons only in the valence shell. By sharing 2 more, it gets 4 only. It doesn't get the octet, but there is no alternative. If you get an octet rule, what is that octet rule? You get 8 electrons in your outermost shell, it's okay. Octet rule is okay, but if it is not possible to get an octet, what is that one can do? I want an octet. If I don't get an octet, I will be satisfied with whatever I get. So, beryllium also has 2 electrons in the outermost shell, valence shell only 2, and that too after excitation the pair becomes unpaired. Originally it is a pair of electrons, and only after excitation, after giving energy, after breaking the pair, it becomes unpaired. Now it has, so apply this, unpaired electrons are used in sharing. Unpaired electrons are used in sharing. So beryllium forms 2 bonds by sharing, and what else it can do? Beryllium forms 2 bonds, example BeCl2, okay, BeCl2, beryllium forms 2 bonds, BeCl2. And what else it can do? It has got vacant orbitals. So if someone donates a pair of electrons, it becomes ready to accept, and it becomes 4. So it will accept 2 more pairs, BeF4 2 minus. 2 pairs, it has accepted 2 pairs. So now what happened? See, beryllium originally has 2 electrons, sharing 2 electrons, it has got 4, and is accepting 2 pairs. So this is the electron of beryllium, this is the electron of beryllium, this is the electron of fluorine, this is the electron of fluorine. These are the pairs of F minus, F minus, F minus. So who is in contact with beryllium? 2 fluorines which are sharing 2 electrons, 2 fluorines which are sharing 2 electrons, and 2 F minus which are donating 2 pairs. So that's how beryllium got octet indirectly. So beryllium to start with forms beryllium fluoride F minus, BeF4 2 minus. So beryllium accept by, so what is the maximum covalence of beryllium? Means whether by sharing or accepting, donating, the maximum covalence happen to be 4. So let us look at the maximum covalency of boron. Boron 2 has 3 electrons only in its outermost shell, 2, 3. Atomic number is 5, number of valence electrons 3. So 2s1, 2px1, 2py1, 2pz0. What is that boron can do? It has 3 unpaired electrons, and I told you unpaired electrons are used in sharing. So boron can share 3 electrons, and it has a vacant orbital. It can accept a pair of electrons. Therefore, the maximum covalency of boron is 4. Examples being boron trifluoride and BeF4 minus. What is boron doing in BeF4 minus? 3 fluorines, 1 bond each, and F minus donates. So the maximum covalency is 4. So look at it at final time. Unpaired electrons are used in sharing and covalent bonds are formed. Paired electrons are excited if possible. So we have applied unpaired electrons to start with. Let us look at the second one. Nitrogen 2s2, 2px1, 2py1, 2pz1. It is important for you to write electronic configuration using the Hund's rule. Means you should not write it as 2p3. 2p3 doesn't tell you anything. 2px1, 2py1, 2pz1, because now it is clear that nitrogen has 3 unpaired electrons, and these 3 unpaired electrons are used in sharing. So, nitrogen forms 3 bonds as in the case of ammonia. Now, what else nitrogen can do? So, we should account for all the valence electrons, what they are doing. Now, it has 2 more electrons, but this being a pair of electrons, this pair can be used only when this is excited. But when the 2s electrons are excited, there is no orbital here, there is no vacant orbital here. We don't expect a 2d here. Okay. Therefore, the pair cannot be excited. So, here excitation is not possible. So, what will you do if excitation is not possible? You donate them. So, nitrogen donates that pair of electrons and forms the 4th bond. Look here, NH4 plus, NH4 plus, nitrogen, 1 nitrogen, 4 hydrogens, one of them is a plus, that is what we learnt in structures, and hydrogen forms 1 bond, and nitrogen still has a pair of electrons it donates. By donating the pair, the shape of nitrogen goes from pyramidal to tetrahedral. That way, the bond angle has increased slightly, 107 to 109.5 degrees. So, the atoms are relatively less strained now. The bonds are less strained now. NH4 plus. That is the reason nitrogen donates that lone pair. So, why are lone pairs donated? The lone pairs are present in a structure, they cause some repulsion. Now, the maximum covalency of nitrogen then is 4, NH4 plus. Look at oxygen, 2s2, 2px2, 2py1, 2pz1. This is the condition of oxygen. What is it oxygen can do in this state? Oxygen has 2 unpaired electrons. They both are used in sharing, and there is a pair of electrons which can be donated. There are 2 pairs, but I have already warned you, even though you have 2 pairs, you can donate only 1 pair. I tell you why. So, the maximum covalency of oxygen is 3. You don't see any substance where you have more than 3 bonds formed by oxygen. H2O, H2O, where oxygen has 2 lone pairs, the pairs remain pairs, and the unpaired electrons which are shared with hydrogen, they are already shared with hydrogen. 2 pairs and 2 unpaired electrons which are shared with hydrogen. So, you count the octet, 1, 2, 3, 4, 4 into 8 electrons. Now, what is this water molecule can do? It will donate 1 lone pair, HOH, H plus. So, there is another lone pair, but that cannot be donated, because after oxygen donates, oxygen gets a formal positive charge. Formal positive charge means we treat oxygen as a plus now. Since it has donated 2 electrons, it is as good as losing 1. Donating 2 electrons means sharing 2 electrons, means is like losing 1 electron, and oxygen gets a formal positive charge. The positive one falls on this oxygen now. So, now it can't donate any further. So, the maximum covalency of oxygen is 3. And look at phosphorus, 3s2, 3px1, 3py1, 3pz1. Similar to nitrogen, the only difference being 3s instead of 2s. Nitrogen belongs to second period, and you know the elements of second period, 1s, 2s, 2p, 3s, 3p. Elements of second period, lithium to fluorine, they have only s and p sublevels, and they have only 4 orbitals, 1 s orbital and 3 p orbitals. So, they have only 4 orbitals, so their maximum covalency can be 4 only. After all said and done, what is required for bond formation? space around the nucleus. If there is space around the nucleus, your electrons can travel along with others' electrons, or both your electrons will be going to another nucleus, or someone else's pair of electrons may be approaching you. So, what is required is there should be some space for the incoming electrons, be it yours or be it others. Now, so second period elements at best can form 4 bonds. But what about this phosphorus 3s2? This is the ground state electronic configuration. Now, what can phosphorus do in its ground state? You see 3 unpaired electrons forms 3 bonds, and there is a pair which can be donated. So, 3, 4. Max in ground state, phosphorus can form 3 bonds as well as 4 bonds. But how is the 4th bond formed? 4th bond is not a normal bond. It is formed only through donation. So, pH3, pH4 plus. pH3, pH4 plus, just like NH3, NH4 plus. This is no new thing. This is only imitating nitrogen, NH3, NH4 plus, ground state. And what else can phosphorus do? Phosphorus in its excited state, when phosphorus is in its excited state, look here, 3s1, 3px1, 3py1, 3pz1, 3d1. Where has this come from? This 3s electron, when some energy is given, it goes to the 3d state. So, what is required for bond formation? Unpaired electrons, paired electrons, vacant orbitals. If pure vacant orbitals are there, you can invite others' electrons. If you have a pair of electrons, you can give them to others. You can donate them to others. So, there are so many ways of bond formation. It is not necessarily losing or gaining as in the case of ionic bond. You can share, you can donate, you can accept. So, considering all these things, the maximum covalency. So, 3s2, 3px1, 3py, 3pz1, we in fact have so many zeros, 3d0, 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 so many zeros, 5 zeros, 3d0, 5 vacant d orbitals are there. So, one of these orbitals is used for excitation. When some energy is given, it goes there like that. So, it's possible for all atoms to form bonds. Even helium also can form bonds for that matter. Helium 1s2. How can it form bonds? Sir, it's a noble gas. It is an inert gas. It doesn't participate in bond formation. Why? The reason for all such things in chemistry is this. Look here. For helium to form bonds, the electrons have to be separated. It is a pair of electrons. Only when it is separated, they can form bonds. For which what is required? 1s1, 2s1. Okay, when you give energy, the pair will get separated, no doubt 1s will go to 2s. This will definitely take place, there is no question about it. When energy is given, who can stop this? The pair of electrons is broken. Now you have got 2 unpaired electrons and now a bond is formed. So, helium also can form helium chloride. Helium can form helium chloride. That may sound surprising to you. It can form helium chloride, but it doesn't form because look at the logic. For this excitation, energy is required. That is, you have to spend 100 calories. 100 calories for excitation. Say. Whenever a bond is formed, energy is released. Can you tell me why? When a bond is formed, look here. Here, the nucleus, only one nucleus is attracting the electron in an atom. Here is an atom, only one nucleus is attracting. This is the electron, orbit of the electron. One nucleus attracting the electron. Suppose another nucleus also happens to come close to this and this is attracted by another nucleus also. Now what is happening? Two nuclei are attracting. The electron comes closer to the nucleus, comes closer. So what happens when the electron comes closer to the nucleus? Energy is released. When the electron comes close to take the electron away, you have to give energy. To take the electron from first orbit to second orbit to third orbit, you have to give energy. But when the electron comes close, it definitely loses energy. Therefore, during bond formation, energy is released. So, the energy released in the bond formation of helium and chlorine is not very high. Say it is only 10 calories per 10 calories. What is that you have achieved? For exciting the electrons, 100 calories have been spent, and when the bond is formed, 20 calories have been released. So, there is a loss of 80. You have spent 100 rupees and you are getting only 20. No fool does it. Therefore, the energy involved has to be compensated in a process. The energy required must be produced elsewhere. Therefore, here, when is excitation possible is very clear. The energy required for excitation, if it is compensated during bond formation. So, it is rather easy to excite the electron here. Phosphorus chlorine bond is formed. When a bond is formed between phosphorus and chlorine, okay, some energy is released. Now you have 1, 2, 3, 4, 5. So, and there are so many zeros, 3d0, 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 3d0. So, phosphorus in its excited state can form 5 bonds, as in the case of PCl5. You know, each chlorine forms 1 bond with the central atom. 5 chlorines, 5 bonds. Now, what else phosphorus can do? Phosphorus we have already seen can form 3 bonds, 4 bonds, 5 bonds. And how can it form more bonds? How can it form more bonds? That is, look here. It has got so many vacant orbitals. Phosphorus got a lot of empty space. Now, if somebody offers a pair of electrons, phosphorus takes and forms 6 bonds, as in the case of PCl6 minus. PCl6 minus. Now, you may get a doubt, sir, there are more vacant orbitals. Why don't you go on accepting PCl7 2 minus? Here, who are involved? Chlorine, 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 chlorine. This is Cl minus. So, one more Cl minus, one more bond, another Cl minus, another bond, like that. Why can't you form PCl9 4 minus? So, after PCl6 minus, you don't see any further accepting on the part of phosphorus. So, the question is, why not more than 6? In most cases, the maximum covalence is 6. Most cases. The rare examples being the halogens, chlorine, bromine, iodine and xenon. Their maximum covalence is 7. Xenon, the maximum covalence is even 8. Xenon can form even 8 bonds. In the case of XeO4, xenon tetroxide, Xe double bond O, double bond O. So, xenon in fact forms 8 bonds. Okay. So, why are they forming 8 bonds and halogens forming 7 bonds, all others maximum 6? In their case, all those electrons belong to themselves. The electrons participating in xenon are the electrons of xenon himself. And IF7, the 7 electrons used for sharing belongs to iodine. Therefore, here you are borrowing, you are actually accepting pairs from someone. So, why not more than 6? The answer is, why even 6? If you ask me why not more than 6, I am asking you, why even 6? PCl5, if you look at it, 5 plus 5, it already has got 10 electrons in its outermost shell. 10 valence electrons, 5 belonging to phosphorus, 1 each from 5 chlorines, 10 electrons. So, you have 10 electrons, PCl5, 10 electrons are there, and even after you have 10 electrons, you are still accepting it, it has to be explained, because If you are short of electrons, as in the case of boron trifluoride, 3 plus 3, 6, okay, it is less than 8. Boron trifluoride has less than 8, and such species are called electron deficient species. Electron deficient. Boron hasn't got the octet, but it had no alternative, therefore it formed BF3. So if a boron trifluoride accepts a pair of electrons, it is understandable. Okay, you will say boron has a shortage of electrons, therefore he is taking from others. But when you look at PCl5, it is an electron surplus, it has got 10 electrons, but why is it still accepting? The answer lies in this 6 will give it octahedral geometry, and trigonal bipyramidal, between trigonal bipyramidal and octahedral geometries, octahedral is more comfortable, more stable, because trigonal bipyramidal is a triangular base. Triangular base, it is some kind of overcrowding. Therefore, in many compounds, you see after octahedral, after forming 6 bonds, they stop accepting any more. Therefore, why not more than 6? The answer is why even 6? Even 6 is to get that octahedral geometry. So, maximum covalency of most of the elements is 6. Now, let us conclude with the chlorine 3s2, 3px2, 3py2, 3pz1. It has got 3 pairs and 1 unpaired electron. How many bonds can chlorine form? It can form 1 bond in its ground state. Suppose 3s2, 3px2, 3py1, 3pz1, 3d1. What is this? This is excited. This pair is broken. This pair is excited. Now you have got 3 unpaired electrons. It can form 3 bonds. So 1 bond as in the case of HCl. 3 bonds as in the case of ClO2 minus. How to draw the structure of ClO2 minus? Look here. ClO2 minus, chlorine is forming 3 bonds. How can chlorine form 3 bonds? This is called first excited state. In its first excited state, that is after breaking 1 pair. Second excited state, break 1 more pair. So excite these electrons also. You have so many D's, 3s2, 3px1, 3py1, 3pz1, 3d1, 3d1. Now you have 5 unpaired electrons, ClO3 minus. 1 more oxygen, ClO3 minus. ClO3 minus. So, as you go on forming bonds, now third excited state, 1 more excited state, 3s2 to 3s1, 3px1, 3py1, 3pz1, 3d1, 3d1, 3d1. So, 7 bonds also, ClO4 minus, ClO4 minus. ClO minus 1 bond, look at this, ClO minus, ClO2 minus, ClO3 minus, ClO4 minus. So, ClO4 minus you indeed have 7. So, chlorine can form 7 bonds because it is not borrowing electrons from anyone. It is using its own electrons. If you use your own electrons, okay, you can form any number of bonds. So, xenon that way has 4 pairs. After breaking all the 4 pairs, it will be able to form 8 bonds. Xenon forms 2 bonds XeF2, 4 bonds XeF4, 6 bonds XeF6, XeO4, 8 bonds, 2, 4, 6, 8. So, xenon shows all these valencies, valency of 2, 4, 6, 8. So, conclusion, maximum covalency of all elements: beryllium, boron, aluminium, gallium, indium, carbon, silicon, germanium, stannum, nitrogen, phosphorus, arsenic, antimony, oxygen, sulfur, selenium, tellurium, fluorine, chlorine, bromine, iodine, and xenon. So beryllium to nitrogen, second period elements, maximum covalency 4. How can beryllium form 4 bonds? 2 by sharing, 2 by accepting. How can boron form 4 bonds? 3 by sharing, 1 by accepting. Because it belongs to third group. How can carbon form 4 bonds? Using its own electrons, CH4. I will supply examples to each. And from aluminium to tellurium, look at a large chunk of them have a maximum covalency of 6. In fact, 4 into 3, 12 elements have a maximum covalency of 6. Chlorine, bromine, iodine, they have a maximum covalency of 7. Xenon 8. Oxygen 3. Fluorine, okay, you can say 2 if you want, you can say maximum covalency of fluorine is 2. How? By sharing 1, by donating 1. Fluorine, you can say 2. Now, let me supply with examples. BeF4 2 minus. What does this tell you? 2 minus means 2 F minuses, 2 donors. There are 2 donors, means beryllium is forming only 2 bonds on its own. 2 own, 2 donation. Boron BF4 minus. So 3 bonds on its own, third group, it can form 3 bonds on its own, 1 by borrowing BF4 minus. CH4, it has 4 electrons, it need not borrow anything, it can form 4 bonds straight away. NH4 plus, for nitrogen it has to form 4 bonds. The only way it can form bonds is it has a pair of electrons and that has to be donated. And H3O plus, oxygen maximum 3. And in the case of aluminium, it is AlF6 3 minus. Aluminium forming 6 bonds. How? You look at the 3 minus. What does the minus tell you? What is the role of a minus in a group? Towards the beginning of the chapter, I told you minus donates. So there are 3 minuses, 3 donors. So 3 are donating, 3 are sharing. Silicon SiF6. How can a fourth group element form 6 bonds? Fourth group element means which has 4 electrons. You have to understand my question. How can a fourth group element form 6 bonds? Means I am indirectly asking you, how can a fellow who has got only 4 electrons form 6 bonds? He accepts 2 pairs, 2 minus. So SiF6 2 minus. Okay. PCl6 minus. Fifth group forming 6 bonds means 1 pair has been accepted from others. Sulfur SF6, chlorine ClO4 minus, bromine BrO4 minus, iodine IF7, xenon XeO4. These are the examples of maximum covalency. You can imitate all others, GaF6G like this. That can be continued. Maximum covalence. Look here. Bismuth 6s2 6px1 6py1 6pz1. All right. What can bismuth do theoretically? It has 3 unpaired electrons. It can share, and in its excited state, suppose the electrons are excited, 6s electrons, 6s1, 6px1, 6py1, 6pz1, 6d1. Bismuth can form 5 bonds also. I repeat, can form. Bismuth can form 5 bonds also if necessary. But the thing is, bismuth is not willing to form 5 bonds. I tell you why. Wait a minute. 6s2, 6px1, 6py1, 6pz1. Suppose if these pair of electrons is excited, 6s1, 6px1, 6d1. So, bismuth in its ground state can form BiCl3, forming 3 bonds with chlorine, BiCl3 and BiCl3. 1, 2, 3, 4, 5, BiCl5. 5 bonds, BiCl5. It can form 3 bonds by sharing and it can also form 5 bonds by sharing, but bismuth is not willing to form 5 bonds. It's not willing. Why? I tell you a little later, but as of now, you just take this statement. Any question on thallium, lead, bismuth, polonium, only these 4 elements, I repeat, thallium, lead, bismuth, polonium, you start thinking in terms of inert pair effect. Think in terms of inert pair effect. What is that inert pair effect? Let me tell you. Inert pair effect. Preferring lower oxidation states and fewer number of bonds. Preferring lower oxidation states and fewer number of bonds is called inert pair effect. Preferring. It doesn't mean that they can't form 5 bonds. Bismuth can form 5 bonds, but it doesn't prefer to form 5 bonds because, okay, let's see why. Preferring lower oxidation states and fewer number of bonds. So, between PbCl2 and PbCl4, lead prefers PbCl2. Between Bi3 plus and Bi5 plus, the lower oxidation state is preferred by bismuth. Thallium, lead, bismuth, polonium, they all prefer lower oxidation states and fewer number of bonds. The reason is, I'll give you the actual reason later, or I think I have already given the actual reason. For any happening or non-happening in chemistry, there is only one reason. The energy involved must be compensated. For anything to happen, if this takes place, that happens, otherwise it won't happen. It is only concern of energy only. Look here, for instance, 6s2, 6px1, 6py1, 6pz1, the energy required to excite the electrons, 6s2, 6s, 2 to 6d. For you to promote the electron, certain energy is involved, and that is not compensated in bond formation. BiCl bond is not very strong, and BiCl bond is not very strong, and not a lot of energy is released. Therefore, bismuth doesn't show any willingness to form, and this reluctance of a pair of electrons, reluctance of a pair of electrons to get separated and participate in bonding, the unwillingness, the reluctance of a pair of electrons to get separated and participate in bonding. This pair is not willing to get separated, in the sense it involves a lot of energy. The energy, lot in the sense, I never mean lot, only relatively. The energy required is more and the energy released is less. So, what happens when more bonds are formed? Energy is released. So, while all other elements want to form as many bonds as possible, for example, phosphorus, will you form 3 bonds or 5 bonds? Phosphorus says I want to form 5 bonds. Phosphorus prefers more and more bonds. The reason being, in small atoms, they are afraid of the lone pairs. The lone pair bond pair repulsions are high. Therefore, the pair has to be separated. The pair will be separated. But in a big atom, BiCl5, big atom, the lone pair can't create much impact on the bond pairs because it's a very big atom. Bismuth is very big. The lone pair can't show. So they are not to be avoided. I said lone pairs have to be avoided. But here, now, so thallium, lead, bismuth, polonium, they prefer to form fewer bonds, and bismuth, Bi between BiCl3 and BiCl5, BiCl3. And look here, PbO2 is a good oxidizing agent. You hear this statement. Why? PbO2 is a good oxidizing agent. You go back to the definition we gave in periodic properties. What is a reducing agent? One who gives electrons. What is an oxidizing agent? Opposites are opposite. Okay. What is a reducing agent? Reducing agent. One who gives electrons. Okay. So what is an oxidizing agent? One who takes electrons. What is the indirect meaning of this? PbO2 is a good oxidizing agent, means PbO2 wants to take electrons. Why? In PbO2, lead is in +4 oxidation state, and in the +4 oxidation state, lead prefers +2. Why? Inert pair effect. That's all. +2 of lead is preferred to +4 of lead 2. So, the consequence, PbO2 is a good oxidizing agent, means PbO2 wants to take electrons so that its oxidation state decreases from +4 to +2. By taking electrons, what happens? +4 minus, it becomes +2. +4 minus 1. Electron means -1. +4 minus 1 minus 1, net +2. So, like that. So, where can you see this inert pair effect? While all other elements, they want to go to high oxidation state, as many bonds as possible. Only these four are satisfied with the minimum number of bonds. Lead says, okay, but no one exhibits inert pair effect in front of fluorine. No one exhibits inert pair effect in front of, means no inert pair effect. So, which is better, BiF3 or BiF5? BiF5. So, this itself proves that the cost involved is compensated. The pair of electrons is broken, some energy is required, and when fluorine forms bond, the bond is stronger. So, the BiF bond and the BiCl bond, what is the essential difference? Small atoms form stronger bonds. BiF bond is stronger than BiCl bond. Therefore, as a result, more energy is released. BiF bond, BiCl bond, more energy is released in this process. So, okay, that's it. Small atoms form stronger bonds. Therefore, what is the actual reason? Despite whatever we say, it is the energy that matters finally. Okay, the energy required for initially, the energy required initially should be compensated eventually. That has to be compensated eventually. That is the essence of anything. Cost price should be less than selling price. Cost price less than selling price. The cost involved must be compensated. That is the economics of chemistry. Now, shapes of molecules. Shapes. We usually have a tendency to invoke the idea of hybridization while discussing shape. Frequently, I get this reply from students. Methane. What is the hybridization of methane? They say, no. What is the shape of methane? They say tetrahedral. When I ask them why, they say it is sp3 hybridization. So, you are indirectly relating hybridization and shape, and I warn you, hybridization and shape are mutually exclusive. They have nothing in common. Because ammonia, hybridization sp3, but shape is pyramidal. H2O, hybridization again is sp3, but the shape is V shape. So, hybridization has not got anything to do with shape. Don't confuse the ideas. Now, shape depends on what? The shape of a molecule depends on number of bond pairs, guest atoms, surrounding atoms, terminal atoms, number of bond pairs and number of lone pairs. That's all. It depends on the number of bond pairs and the number of lone pairs. So, most importantly, before we try to find shape, we should find the number of lone pairs. How to find? What do you mean by number of lone pairs? Number of unused electrons in bonding. How many electrons are not being used? Look here. Number of valence electrons of the central atom. Of course, we are always interested in the central atom only. Number of valence electrons of the central atom minus number of electrons used in bonding by 2. It means how many you have spent and how many pairs are remaining, as simple as that. Number of valence electrons, how many you have, and number of electrons used in bonding, how many you have used in bonding. For example, let me find out the lone pairs in SnCl2. What about this? 4 minus 2 by 2. Stannum belongs to fourth group. From the beginning of this topic, I have been warning you to know which element belongs to which group. The moment I say stannum, if your fourth group comes to your mind, SnCl2, 4, 2. So there is a lone pair. 4 minus 2 by 2, 1 lone pair. NH3. So you take a host of molecules and practice all these on this. Don't do hundreds of questions. Instead of doing hundreds of questions, I will give you a host of molecules. NH3, BF3, CO2, SnCl2, SiCl4, SnCl2. Like this, you take so many molecules. SO3, XeO4, XeO3, XeF2. So, some 60 molecules are there in our syllabus. What you should do is find their hybridization. Find the hybridization of all. Find the shape of all of them. Find the number of lone pairs in all of them. Find the number of sigma bonds in all of them. So roughly 60 molecules into 10 questions, 600 questions will be covered on a sheet of paper. Okay? For example, find out everything about SO3. Everything you know. SO3. 1 sulfur, 3 oxygens, like this. So what is it you know? 1 sulfur, 3 sigma bonds, 3 pi bonds. Then oxidation state of sulfur is equal to +6. So instead of answering questions like oxidation state of sulfur in SO3 is, oxidation state of boron in BF3 is, oxidation state of, instead of answering individual questions, you find the hybridization of 40-50 molecules, shape of the same 40-50 molecule, hybridization, shape, number of lone pairs, all things on the same molecule, like this. Then what about SO3 shape? Planar, trigonal, planar. And hybridization 6 minus 0 by 2. What is that? 3, sp2. Number of lone pairs? No, 3 bond pair, 0 lone pair. Like this, any number of questions can be answered on the same. So NH3. Find the lone pairs in NH3. Nitrogen belongs to fifth group. 5 minus 3 by 2. There is a lone pair. Like that. How about SO2? SO2. 6 minus 4 by 2. What is this 6? Sulfur, you know, belongs to the sixth group. Minus 4 by 2. 6 minus 4 by 2. 1 lone pair. SO2. Like this. So, the shape of a molecule depends on the number of bond pairs. You may be mistaken It is not number of bonds I am not talking. It is number of bonded atoms. Number of bond pairs means number of atoms that are coming to form bonds. Whether they form one bond or two bond, it is the number of guest atoms, number of bond pairs, number of lone pairs. Look here. 2, 0. What do you mean by 2, 0? 2 bond pairs, 0 lone pairs. The shape is linear. 2, 0 linear. 2, 1 bent or angular. 2, 2 V shape. 2, 3 is also linear, unexpectedly linear. So many lone pairs are there, but still linear. 2, 3. What do you mean by 2, 3? 2 bond pairs, 3 lone pairs. Now, 3, 0. Trigonal planar. Trigonal planar. 3, 1 pyramidal. 3, 2 is a T shape. 4, 0. 4, 0 is tetrahedral. 4, 1 seesaw or distorted tetrahedral. Distorted tetrahedral. Seesaw. 4, 2 square planar. 5, 0 trigonal bipyramidal. 5, 1 square pyramidal. Square pyramidal. 6, 0 octahedral. 6, 1 distorted octahedral. Distorted octahedral or capped octahedral. Capped octahedral. 7, 0 pentagonal bipyramidal. Pentagonal bipyramidal. Now, so when I ask you the shape, don't tell me the actual shape. You just mention 2021 like that. SNCl2. I am even marking the lone pairs. You need not even find lone pairs now. I have already marked the lone pairs. You just tell me it's 2, 1. 2, 1. I will mark the lone pairs ahead of the formula itself. Look here. Means by the time I write the formula, you must be able to say 2, 1 because you have already seen the 1. You have seen the 1 ahead of 2. 2, 1. So what is the shape of SO2? 2, 1. So if you know the lone pair, I have marked the lone pairs here. So what is it you have to learn? You should be able to mark the lone pairs yourself. 2, 1. BF3. There is no lone pair. 3, 0. 3, 0 trigonal planar. You need not tell me trigonal planar because if you say 3, 0, I understand as much. Understand. So you just tell me the coordinates. CH4. There is no lone pair here. 4, 0. Because I am marking the lone pairs if any. If there is a lone pair, I am marking you. So you need not trouble yourself. The next part I will ask you to mark the lone pairs. 4, 0 tetrahedral. What is it you are seeing ahead of the number? 1 lone pair. 4, 1. 4 bond pairs, 1 lone pair. 4 bond pair, 1 lone pair. Seesaw or distorted tetrahedral. So what is the conclusion? The shape of a molecule depends on the number of lone pairs and the number of bond pairs. And listen, you just find out the lone pairs this time yourself. XEF2. 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 How to find out? X minus 2 by 2. 8 minus 2 by 2, it is 3. 1, 2, 3. 8 minus 2 by 2. XEF2. Okay? 2 bond pairs, 3 lone pairs. 2 bond pairs, 3 lone pairs. Linear. Despite the presence of lone pairs, it acquires a linear shape because the lone pairs cannot be avoided. There are too many lone pairs, even if the atoms try. Okay, they will be taking a linear shape, and the lone pairs are in the equatorial position. The lone pairs are in one plane, and bond pairs are above below the plane. Like that, you can take your own example and you can find yourself XeO3, 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 8 minus 6 by 2, one lone pair. XeO2F2, the shape of XeO2F2, question given in 2012, IIT 2012, this question is given. The shape of XeO2F2. How to find out? First the lone pairs. First things first. 8 minus 4. What is this 4? 4 electrons are used by oxygen. 8 minus 4 minus 2 by 2. 8 minus 4 minus 2 by 2. There is one lone pair. Total number of, guess how many? 2 oxygens, 2 fluorines. So it is 4 bond pairs, 1 lone pair. XeO2F2. This is called distorted tetrahedral or seesaw. Seesaw. It's something like this, a V shape. On a V, you draw a line. Seesaw, XeO2. Don't worry whether oxygens are in this plane, oxygens are at this position, or oxygens at this position. That's not very important. Okay, that is secondary discussion. That is all secondary discussion. You need not waste time on it. Enough if you know seesaw. Where exactly on the seesaw the atoms are arranged. Now, SOCl2. Find the lone pairs and bond pairs. 6 minus 2 minus 2 by 2. 6. What is this 6? 6 electrons of sulfur, 2 of oxygen, 2 of chlorine. 6 minus 2 by 2. So there is still one lone pair sulfur. So how will you draw the structure? We have already learned drawing the structures. SOCl2, 1 sulfur. Why is it pyramidal? 3 bond pairs, 1 lone pair. Like ammonia. So ammonia, SOCl2 or SOF2 for that matter, SOF2 or OSF2, ammonia, XeO3, all these are isostructural. What do you mean by isostructural? Same shape, that is same number of bond pairs and lone pairs. Same number of bond pairs and lone pairs.